I'm excited to do a follow-up to our first AI podcast. And I'm hoping that you can enlighten us a little better on now like deep learning, especially with everything going on with ChatGPT 4. I know one of the things we wanted to talk about was large language models. So awesome. Welcome, Jack.
Thank you. Thank you for having me.
Why don't we get right into it? Like, what is machine learning? And remember, we're talking to people who are not generally computer programmers.
Yeah. So I know we talked about it a little bit in our last podcast, but I want to make the distinction of machine learning versus classical artificial intelligence, which has really been studied since computers were first invented. So the field of AI has a big branch split. One of these branches we call classical AI. Sometimes it's called good old-fashioned AI, and the other branch is traditionally, historically called connectionist, or they're machine learning practitioners.
Okay.
The classical AI approach is just writing exact algorithms to solve your problem. They're algorithms that you fully understand.
That's my favorite kind of stuff, because that's what I did forever, which was take a paper algorithm and then just write hard-coded rules that told the system exactly what to do.
Yeah, so the best example, like an easy example of this is like pathfinding. Like there are algorithms for if you have some maze, and you have a cost for traversing different tiles in a maze, like in a video game.
Okay.
There are algorithms for, finding like the shortest path between 2 points, taking into account that there might be some cost to like jumping over a river or something like that. And that would be a classical. I mean, they're classical algorithms, like to some degree.
But it's still learning. It's still a system that learns because it has
it's not a system.
So how does the cost function work in that setting? If it's like classical?
Have algorithms that just they precisely solve your problem. The system is not learning over time.
Okay.
You just exactly tell the computer what to do in every situation.
Okay.
Another example is the chess playing AIs.
Mm-hmm.
So for a long time, before the 90s, I've heard that people in the field used to say, oh, an AI that could beat humans at chess would be like the pinnacle of AI achievement.
Right.
Because we couldn't do it for so long. I believe Alan Turing, even when he was inventing the notion of the modern computer, he actually tried to write some chess playing programs like in the 40s, and he did. But all those approaches were classical approaches where usually you would consult with human chess experts. And you would say, hey, what pieces should I tell the computer to value more? You tell the computer that a queen is valuable.
Okay.
More valuable than a bishop or a knight.
Okay.
And you give it a heuristic function to say, if you look at the board, I think you should estimate that the board has a certain value. But you are telling it how valuable the board is.
Okay.
Those approaches actually worked because in 1997, IBM's program beat Garry Kasparov using a classical approach.
Right. Okay.
The reason why the computer was better was because it can search tens of millions of moves into the future, all these different considerations of what, it like classical approaches are better than humans at chess.
Okay.
But the system did not learn.
Right. Okay.
And it potentially has the drawback that it's limited by the guidance the humans gave it. Even a human chess master may be flawed compared to optimal chess play. And actually, it definitely is, because today, like, the chess AIs are essentially oracles. Like they're always better. Magnus Carlsen, the current chess champion, has a 0% chance to beat any, good chess AI.
That's amazing.
And now we take it for granted. So this is a really interesting story of AI progress.
Yeah, through chess.
This happens. We're going to talk about this when it comes to large language models later. But there's a long period of time where people go, there's a certain camp of people, they go, AI will never play chess because humans are special. The human brain is special. Computers could never possibly understand the intricacies and the intuitions you need to play chess.
Right.
Then computers beat the human master at chess.
Right.
And then people go, oh yeah, I never said I would be impressed by that. Obviously the computer would be better at that. And then they say, oh, but the computer will never do this other problem. And then we wait 10 years and then the AI, and then we solve that problem.
And that amount of time keeps getting shorter and shorter, actually. Things are moving so fast.
But
I mean, it brings us to the AlphaGo discussion, but I mean, go on. Go on from classical AI. Finish that concept. I want to hear.
So there is a little bit of a gray line. There's a little bit of a gray line between classical AI and just traditional algorithm development in computer science. Because in computer science, we have a lot of algorithms. An algorithm is a set of instructions that a computer can follow. And we have very rigorous ways of understanding how fast algorithms can run, how the runtime scales with the input size. And there's whole fields of study called computational complexity theory, where the whole point is, how long do algorithms take to run? We're mathematically analyzing the properties of algorithms.
The kinetics.
It has nothing to do with how powerful your computer is. It's like inherent to the algorithm itself, these properties.
Right. And you can write smart algorithms. I mean, you know that. You see somebody write a smart algorithm, it can run so fast, but you can get the job done with another algorithm, but it could take forever.
Yeah. And so we would call that, it's just more efficient.
Right. Efficiency.
And yeah, you want to get the bound as low as possible, like for, how slow you're possible, or how slow, what's the worst case for your algorithm? You want that to be as fast as possible.
Right. I hear you.
So we don't usually call those algorithms AI, right? Like most computer scientists are not necessarily studying AI. So classical AI, I think the reason it's called AI at all is because of the problems they try to solve. It's because they're trying to solve like something like chess, where we would say, well, if you can play chess, clearly you're intelligent.
Right.
Kind of traditionally, we would say something like that. So because they're trying to write explicit algorithms that play chess, they're calling it classical AI because the behavior it's exhibiting is something that we would normally attribute to only like intelligent beings. So yeah, the crucial notion of the classical AI is that the computer is not learning and the human developers are explicitly giving it a set of rules.
Yeah, so there's a set of instructions there. The computer's following it. It's doing it super fast, so it does improve efficiency to what we do, but it's not like the computer is showing us any insights or doing anything in a smarter way or advancing anything better than the best of us could do.
Yeah, you're exploiting. The only reason it could be better is the fact that computers don't mess up.
Right.
They do exactly the instructions you gave them, and they can, again, like, in the case of games, they can just think much farther in the future, because we can only keep a certain amount of, you can only simulate your own gameplay a certain number of moves into the future before you run out of space in your head, and a human can't simulate like a million moves in the future, but a computer can. So even though you programmed it, it does better. But I think this is a good segue into what's the difference with machine learning from classical AI.
Yes.
And there's a particular formal definition of machine learning that I like. And it just says, you're doing machine learning if your computer program is getting better at some task or set of tasks. So you formally define a task or like a problem.
Mm-hmm.
The notion of getting better must be attached to some formal measure of performance. Okay, so you have a task and you have a performance measure, and the computer program gets better as it gains more experience. That would be training data.
Okay.
Either training for longer or training, with more data. And machine learning is really a subset of AI.
Right.
So, all machine learning is AI because you're trying to solve, you want the program to exhibit intelligent behavior, things that we thought only humans could do. We want the computer to learn how to do.
Right.
Recognizing what objects are in images, like looking at an image and saying, I know this is a human face.
Right.
Okay, our iPhones do that when they put the boxes
right, the
around
little box, the face
human
finder.
face. They're using machine learning for that, presumably. I'm pretty. And self-driving cars like Tesla, it has tons of machine learning running within it to recognize what objects it's seeing outside of its, it's seeing with its cameras.
Right.
And
so that's machine learning. The system is getting better at a task, and by performance measures, we can see that this thing is improving over time. So
yeah.
So how about deep learning?
Yeah. And just to stay on that point, one of the amazing powers that once you start doing machine learning, you unlock is that the computer can learn things that you did not expect. So this is where doing machine learning gets fun and starts getting mysterious, because all you do is you kind of set it loose on your problem. And
right. It's incredible.
You might be surprised at what it learns.
And the thing is we're going to talk about this because we don't really know what it learns, because there's no way. Well, I want to understand that better. So let's talk about the learning process, or go on from there.
Let's break down the learning process a little bit before we even get into deep learning, because deep learning is just a special case of what we're talking about.
Okay.
Right. Everything I'm about to describe about the machine learning training process, it applies to deep learning, but deep learning is it's more particular, more specialized in what we're doing.
Okay.
But
how does learning work? How does a computer made of equipment learn something?
So let's say we have a whole data set of images. 50% of them are images of cats and 50% of them are images of dogs.
Okay.
We want a program to input an image and tell us, is this a cat image or a dog image?
Okay.
This is a great machine learning problem because it's extremely difficult to write an explicit algorithm that solves this problem. I mean, it's almost impossible. Like no one can really do it, because there's so many, when you get into the image space, there's so many variations of what, like, first of all, where in the image does the particular cat face appear?
Mm-hmm.
Is it in the top right? Is it in the bottom left?
Right, right.
So, if I ask you to write me an algorithm that detects like a cat ear, how do you even begin doing that?
Right.
It's unreasonable to like think about
to hard code that.
And also there are cats with no ears, like, and it'd still be a cat, right? So there's so what do you do? So this is a perfect case to try out machine learning. So we have all these images of cats and dogs. We call that our training data.
Okay.
And we want to label each image. Let's assume we have the labels for each. So we have the images of cats. And with those, we actually have annotations that say, this is an image of a cat.
Okay.
And with an image of a dog, we actually have an annotation that says dog. So we have the right answer.
Okay.
Then you take your favorite machine learning algorithm. There's a whole bunch of them. that are not deep learning. There's a whole bunch of them, but it could be a neural network as well. And you define a loss function, which says how badly is my machine learning model doing currently. And so it gives you a quantifiable measure of how good or how bad
how
you're
far
currently
off
doing.
it was. But it could
That
only
is
be
crucial.
said it was a cat or said it was a dog, right? Or the cost function.
So the loss function is...
Or the loss function.
So this is what we would call a binary classification problem,
Right.
which means there's two possible categories.
Right.
And so the output of your model has to be, it just must be, you have to be able to interpret the output of the model as, cat or dog.
Or dog.
Yes or no. Yes, cat, no cat.
Right.
However you want to think about it. And so the loss function has to somehow take that output and say, okay, I predicted it was a cat, but it was actually a dog.
Okay.
So that needs to be a bad loss.
Right.
It's going to be a high loss because, it's very bad. If you predicted cat and it actually was cat, you want a low loss.
Okay, I see.
The reason why the loss might be a little more nuanced than just,
cat
yes,
or
cat,
dog.
Yes, cat, predicted cat and it was a cat, predicted cat and it wasn't a cat, 4 different options, is because usually the output of the model will be a probability. And so it might say 90% cat.
Okay.
And if the answer was, it really was a cat, that's pretty good. And so the loss will be relatively low. But if it says 10% cat and it was a cat, that's really bad. And so as the model learns, as it iterates over this training data, you want the probability output to match up as well as possible with the
gold
list
standard
of labels.
answer. Right.
Yeah. So, the learning process is, with most models, you have on every iteration over the training data, the model is able to update its own parameters, which change its predictions. And we have ways to update the parameters in ways that make the model better next time. So you can think of the loss function like, in a very simple case, a parabola, like a U-shaped curve. And when you first initialize the model, it'll do very badly on your problem because it hasn't learned anything yet. So on this loss function landscape, which really is going to be in a very high dimensional space, you could think of it, you could really reduce the complexity and think of it like even a 3-dimensional bowl shape. Okay. Just for visualization. And when you first initialize the model, where it is on this loss landscape will be somewhere far away from the minimum. And we use calculus in the iterative learning process. Even for some simple machine learning models, we can calculate the slope or the derivative, or in high dimensional space, we call it the gradient of this loss function, which tells us what direction does the model need to update the parameters in order to make the loss go down.
Right.
And so when we say that this process is called gradient descent, what we're literally saying is you're following the gradient in the negative direction, which is like standing on a mountain, slope and going down the direction of steepest descent.
Right.
So you look directly down at your feet and you say, where is the grass where's the ground going down the quickest?
Right.
And that's the direction you step. And if the model gets really low, if it gets close to the lowest point in this landscape, that corresponds with solving the problem very well.
Right.
Or perfectly.
Right. But going back to that for a second, because I think it's the image one is a good example to understand, and you can explain this better, but it's not just like it looks at the image in one big view and goes, okay, cat. it kind of breaks the image down. And
This depends on what model you're using.
okay, so
some of the machine learning models just look at the whole thing and
really,
they just give an output.
okay,
Yeah.
yep,
Like there's a simple one called K nearest neighbors. What this algorithm does is it literally calculates a distance between points. When I say a point, I mean like an image is a point.
okay,
Like you can consider an image of a cat as a single point in a very high dimensional
right, exactly,
space of
Got you.
images.
Of infinite dimensions, right?
Not infinite dimensions.
Just
it's
as many dimensions as
the number of dimensions is exactly known as the number of pixels.
right, the number of pixels. Cool.
And also, and we might have art, and on computers, images have 3 channels, RGB.
Right.
And so an image is actually,
some
the number of
combination of
pixels
those.
times 3 for each RGB value. And so you add all those up, that's the dimension of your input space. Okay.
So depending on which algorithm, which machine learning program you use, it has a different approach to it.
Yeah, because you can actually use the fact that you can consider this image as a point in a high dimensional space.
Okay.
You can use that fact to literally calculate the distance between 2 images. And what K nearest neighbors does is it says, I'm going to look in the training data and look at the distance between I'm going to look at the points near me that are the closest. And I'm just going to say that I'm the same label as them.
Oh,
it does a majority vote. So you can say, I'm going to look at my 5 closest neighbors in the training data.
I see. So if there's 3 with cats, like in those labels. Right. Okay.
So if 3 of the 5 closest points are cats and the other 2 are dogs, I'll just say this image is a cat.
I see.
And so that's one that just directly uses all the...
It's like a comparator.
It calculates a distance between 2 images, and it directly gives you a classification for any image.
And the more training data you have, the better that one will do. Well, because...
That's what you have to find out.
Yeah.
We can't really say... We can't always make scientific claims like that about the process. And that's one of the issues with this field is you really just have to try it. You can't you can't always predict what's going to work and what doesn't. You just have to try it. Right. It's almost like it's more close to the scientific method where it's like you can come up with a hypothesis, but you really just have to empirically test it.
Okay.
Because we don't have solid mathematical theories of loss function landscapes or of how these models learn or what they learn or when they will successfully learn. We do not have rigorous mathematical theories about this, which is why the field is so driven on empirical results.
So that's the concept of of machine learning.
Yeah. So yeah.
And using an image as an example. What are like other, other than a pixel, like a picture, which we can all, that's easy for us to understand. What other things are kind of used where they apply deep learning? We have,
or machine learning.
Or machine learning.
Even. So this is really, again, the power of machine learning is that the input, as long as you have a set of numbers, you can try machine learning on your problem. So this is why you could train a machine learning model on medical data and predict medical outcomes if you have inputs that you can reduce to numbers. So like, you have patient data, male or female, right? 0 or 1.
Right.
And then you have all these values of blood work, let's say, things you know way more about than I do. And you can just plug all these numbers in to the input. And if you have something you want to predict, you can run this process on medical data.
If you have a known output, like you have a known outcome, and then you have training data where you apply all your medical data, and then you run it through your machine learning algorithm, and you teach the system, and you see how good it is at predicting now with new test data.
Yeah, so I think like some of the most popular fields that machine learning are applied to are image processing, like we talked about, the medical field for sure, natural language. So trying to either generate language or just understand language, or, you know, like translation between languages. These are things you can apply machine learning to. And those are, I mean, you know, between natural language and images, those are two of the biggest research areas within ML.
DALL-E and ChatGPT.
Yeah, we're definitely going to get into that too.
No question about it.
So, you know, I think we should get into deep learning.
Let's do that.
Because we said that machine learning is a subset of AI.
Right.
Now, deep learning is a further subset of machine learning.
Okay.
But in deep learning, we're talking about a particular class of models that are deep neural networks.
Okay.
Now, deep neural networks have been around since before you were born. So in the 50s...
There were computers before I was born? No, just kidding.
In the 50s, really the first notion of like a deep neural network was invented. Frank Rosenblatt, I think it was the late 50s. And he wrote a paper on something called a multi-layer perceptron. And what this is really the most vanilla kind, the most basic kind of neural network that we still use today. The simplest kind is where...
It's the single functional unit of a neural network, right? Because I think of the brain, we think of like our machine learning, and when you learn about how neurons work, it is the neuron, which is the single cell that is able to communicate. You know, it has a cell body, it has an axon, and then it has the parts that output to other neurons or muscles. But that's how our learning happens. And so the perceptron, I think, is the single functional unit of a neural network.
I want to be definitely careful about saying confident, like this is how we learn, because we really don't know that. And we know, actually, I think we do know that like the way artificial neural networks learn are not the way the human brains learn, but they are inspired by
right.
them.
And what I mean by it is not exactly how it learns, but what I'm saying is the functional unit. Like in the kidney, we have all these filters, but if you take one out, it's called a nephron. That is the single, but 2 million of those is 2 kidneys. You know, each kidney has a million.
Right.
In the brain and the nervous system, we have all this, you know, neural system, but it breaks down to a neuron. You know, that's
I think...
Is the perceptron like that? What defines a perceptron?
Well, a neuron is really the most simple kind. And we can define some terms. So when we say multi-layer perceptron, we're talking about really the simplest kind of deep neural network.
Okay.
And what a deep neural network is it's a collection of what we call neurons. Okay, so when these were first invented, they're inspired by the brain.
Okay.
So that's why it's called a neural network, because it was loosely inspired by how people thought the brain worked. But I can't speak to the brain, so I'm just going to talk about how the artificial neural networks work.
Okay.
A neuron really is just a node that holds a number. So when I say neuron, you can just think a real number like 3, 7, a million, 3.14159. It's what we call a floating point number in computer science. And you have layers of neurons, and each successive layer is connected to every single neuron in an adjacent layer.
Okay.
So if you're in your first hidden layer and you look at the first neuron, it's connected to every single neuron in the previous layer, and it's connected to every single neuron in the successor layer.
Okay.
Yeah. And
now the first layer going into a neural network, that is your inputs.
Yeah.
I mean,
so the first layer we call the input layer.
Okay.
It just contains all of your inputs.
Okay.
So all the data that's relevant to your problem that you want the network to incorporate it, you know, to use that value in order to help it predict something
Okay.
goes into the input layer.
All right.
And in the simplest case of a multi-layer perceptron, let's say you have one hidden layer. So, we use linear algebra to batch all these computations together, and we take the input layers. The multi-layer perceptron has a set of parameters that influence the particular values that the neurons take on. So these parameters are also called weights.
Right.
And when you hear like a weight in neural network, really that's just also a number.
Okay.
Like 7.3, 2.1, negative. They can be -3.
Mm-hmm.
And so you can think of a simple neural network as having a collection of tuning knobs, like little radio dials.
Right, yes.
However many parameters you have, every parameter is a single dial. And these dials exactly determine what the output, along with what the input to the network is.
Mm-hmm.
The input and the dials exactly determine what the output of the network is. And so the goal of machine learning in general and deep learning is to find the exact specific tuning of all of these dials that solve your problem. And when I say solve your problem, I mean the neural network has an output layer, and there's really two different cases. Either you're doing regression or you're doing classification. Okay. Regression means you're trying to predict a single number, mm-hmm. like a house price.
Okay.
So let's say you use machine learning, you input the square foot of your house, how many acres you have outside, how many bathrooms, bedrooms, all numbers, right? You input right. And you want to predict a housing price.
Okay.
Well, that housing price could be really any number, right? It could be $1 million. Right. It could be 300,000, 700,
Got it.
Or you can have classification, which mm-hmm. is I want the network to predict that the input sample belongs to a number of discrete categories. Like, is this a cat or a dog? Or is this image of a lung cancerous or not cancerous? Or is this doing optical character recognition, like looking at a PDF file and saying, is this character the letter A or B or C? This is also a classification problem. And so neural networks were invented a long time ago, is my point. But people did not realize that they were useful. In fact, there was somewhat of an AI winter back then, where there was a bit of a stagnation of neural network research because people just thought they didn't work very well.
Right.
And do you know why they didn't work very well?
No, tell me.
It's because our computers were not powerful enough yet to actually train them on enough data to get them to learn interesting things.
Mm.
So we've had the notion of neural networks, but then in 2012 was really the deep learning revolution. Mm. This was when a new specialized type of neural network was invented called the convolutional neural network, or a CNN.
Right.
And CNNs were very good naturally at doing image processing.
Mm.
Right. For particular mathematical reasons, they have biases within themselves that make them super attuned to recognizing objects within images.
Okay.
And they started doing well in the field, like shared benchmarks of, object recognition, image recognition, like recognizing human faces within images, mm-hmm. Classifying just arbitrary objects. Like, is there a plane in this image? Is there a chair, a car, a train, a bus,
We're not even that good at that with CAPTCHA. It's like,
well, that's the interesting thing is naturally we are very good at like
pattern recognition,
at facial recognition.
That's true.
We're actually so good that we see faces where they're not actually there. Mm-hmm. Right? We see them in rock formations, cloud formations.
That's so funny.
We're almost too attuned because presumably it's better evolutionarily to be a little conservative, to think like,
oh, that's
probably a face, just in case it's going to attack me, right?
Oh, yeah, right. Oh, that's funny.
Like, it's better to think that every rustling in the bush is a lion even if it's not,
Mm.
then the one time you say it's not a line and it is, right?
Yes. High
So,
sensitivity.
so 2012 was really the revolution where people realized, wow, neural networks are actually working, particularly for images.
Mm.
And that's because finally our computers, we had to wait for the computers to get
catch
powerful
up.
enough
Mm.
to run them with the requisite amount of data, with the requisite number of, the requisite size of the model too.
Mm-hmm.
So, an important point is that when you create a neural network, you are the architect. You can make it as big or as small as you want.
You decide how many layers and how many nodes per layer and all of those
Yes.
details.
I mean, we literally call it a neural network architecture. Like if you come out with a new neural network, people say, oh, what's the architecture?
Oh, that's interesting.
Well, it's this type. Let's say it's convolutional.
Okay.
Which, let's just say it's good at processing images.
Okay.
It has this number of layers, these types of layers, because when we say layer, there's actually many
when
different
they say
types of
convolutional, what does that mean? Convolutional network.
Convolution has a particular mathematical meaning.
Okay.
And it, you can roughly think of it as kind of like moving a sliding window over an image and taking an average of the pixels around it.
I see.
And this window can be, if it's trained well, it kind of contains parameters that allow it to determine features of the image. But the cool thing about them is that they can kind of learn what features they need to automatically.
Mm.
Like when you set off a convolutional network to, let's say, recognize human faces within images, they will on their own, or they can on their own, come up with feature representations of like a human ear. Like, oh, here's where the ear is. Here's where the nose is.
Mm.
And it did it for you. Like going back to what we said before, you couldn't write an algorithm. Like
that would
I couldn't
be able
write
to
an
do
algorithm to detect a human ear. But the convolutional network does come up with, it figures out from looking at the data itself.
Right.
What is a good representation of the human ear and how can I detect it when I see one?
And it kind of like, from what I was looking at in terms of the image convolutional networks, it sort of starts off with the most basic things like lines, and like the earliest hidden layer is very, very raw data of horizontal, vertical lines. And then as you move through the layers, the organization of the features of it become more characterizing of different features of it in large scale, like ear, nose, mouth, eyes, and then face, so it's...
You can think of a neural network as really performing a computation over your input. And so with a convolutional network, right, it can initially, like a single convolution can detect, like you said, an edge. It can detect a vertical edge or a horizontal edge. And you can combine these that with subsequent convolutional layers, you can combine these to represent more complex images, or kind of arbitrarily complex patterns within the image. But a neural network really is just a computation. It's a mathematical function that's built from a bunch of tinier mathematical functions.
Mm-hmm. So tell us understanding neural networks a little bit better, how does it change like its weights? What does it do? Like, how does it function as it's learning on a training set? What is the process of learning in a neural network?
So neural networks have two modes they can operate in.
Okay.
And let's talk about the first one, which is just forward mode.
Okay.
Or inference mode. This is where the neural network takes input data and maps it to an output.
Okay.
So we're not talking about learning just yet. How does a neural network actually just map an input to an output? That's why it's a mathematical function, because it just maps an input to an output. The neural network is composed of a bunch of tinier math functions. One of these simple functions we call the linear layer. And this is literally just a linear computation, where you multiply all of your inputs by a big weight matrix, which are the neural network's parameters. And what that produces is matrix vector multiplication produces another vector, and that output vector is the next layer, is the values of the neurons in the next layer.
Okay.
But the problem is if we only composed a bunch of these linear layers on top of each other in order, the output you would see is still just linear. So let's say you just put a bunch of linear layers next to each other. You run data through the network, and your output is just a line separating your data.
Right.
So if your data is more complex than,
then can be described by a linear.
Yeah. So what I mean is, like, if you have a bunch of dots over here and a bunch of dots over here, and you can separate them by a line, we say that your data is linearly separable because a single line can give you a classifier for
who's who, for categorization.
You say if you're on this side or if you're on this side,
exactly.
You can determine a classification. So if you have only linear layers, that's actually the same thing as just having a single linear layer. And the reason for this is if you compose linear functions within other linear functions, the output is just another linear function.
I got you.
So what we do to make neural networks able to represent more complex patterns is we have to introduce non-linearities, and we do this in terms of activation functions. So an activation function takes the output of multiplying all the weights by all the inputs, and it maps it through a nonlinear function. The simplest nonlinear function we call ReLU, or the rectified linear unit. And you can think of that as just, it is the line y equals x, except if the input is negative, it maps it to 0.
Okay.
So what the function looks like is if your input is negative, it's just a flat line
on 0.
And then it becomes just a line after that.
Okay, I see.
So it's
linear up to 0.
Yeah,
because it is linear until it hits a negative number, until it hits 0.
Of it is linear, but the function overall is nonlinear.
Yeah.
And what's amazing is that even that simple function unlocks the power for a neural network to really, like, if you stack a bunch of these layers on top of each other, represent really complex relationships.
That's amazing.
And
so is it just trial and error to decide what activation function you're going to use? Or do you somehow look at your scatter plot of all this data to say, oh my God, we have stuff all over the place. We're going to need something more complex, to be able to separate out these.
It doesn't really matter. Like as long as you have a nonlinear function, what we found, like, there are differences between the activation functions. And yes, there are a whole host of them we could use. I mean, you could use an exponential function. That's not linear. You could use the ReLU. You could use a sigmoid, which actually is often used, which is just like an S curve.
Right, exactly.
Right? That's definitely not linear.
Right.
And people do use these different ones, but it's really more of an art than a science. And this is the story with architecting any neural network right now in 2023 is it's more of an art than a science. And if you ask the leading researchers why they made their model exactly the way it is, the answer will usually be something like, I just kind of did it and it worked. Right. I mean, we're getting better with determining what works and what doesn't, but we definitely don't have an exact science for, if you want to solve this problem, you should use this many neurons and you should use this activation function. It's really the Wild West of research right now.
That's amazing. That's awesome.
But a single neuron, I think it's almost useful to break down, because when I'm talking about the linear algebra computations of this forward mode of the neural network, I'm talking about really batching all of the computations together into one. But if you zoom into a single neuron, how do you get the value of that neuron? You take the weight that's going to the previous layer, and you multiply it by the value of the neuron in the previous layer. So you're really just doing like neuron times weight.
Yes.
And then you get the next neuron.
And then you sum those up.
And then you sum them all the contributions from the previous layer, you sum them all up.
Right.
You get a single value. Then you pass it through the activation function, you get another value.
Yes.
And then you just keep doing that. That's it, really. And then you can do as many of those as you want. And finally you get to your output.
And that's how it moves forward. It propagates forward through that perceptron or through that neuron.
Exactly. So these simple neural networks, they only go forward.
Okay.
And that's why they're also called feed-forward neural networks, because the data propagation only goes forward. And so we get our output, right? But now we want to train the network.
Yes.
So
if it only goes forward, you just get what you get. But the system doesn't get better.
Exactly.
Okay.
If all you had was forward, the system never gets better.
That's it. Right.
So, and when you first initialize a neural network, usually, literally, we randomly initialize the weights between like -1 and 1. We just say, hey, just randomly, we randomly initialize the parameters or the weights. And, you'll get -0.7, 0.5, 0, just all these, it's a soup of numbers. And by default, your model's not going to know anything. It's not going to know how to solve your problem. So we need an algorithm called backpropagation, which is the backward mode of a neural network. This is where the learning happens.
This is the magic. This is the slap of the hand.
Yeah.
Don't do that again.
This is where, when you have your loss function, which tells you how poorly the network is performing, you use calculus to determine the gradient at the neural network's particular setting. You iterate over all the training data and you say, what direction do I have to update the parameters in to make the model do better next time? And we can do that.
It's amazing.
We essentially say, what direction do I go in and how far? That's the step size, the step length.
Right.
And you keep doing that and you converge on some local minimum to the function.
To the cost function. The loss
function.
Right.
Yeah, same thing.
Same thing. Right.
And, I mean, the interesting thing is that loss functions are usually for complex problems. They're what we call non-convex. So a convex function is, you can think of like a bowl. There's at any point where you are, you can kind of just slide down and you'll reach the global minimum.
Right.
But in a neural network, you can think of it as like a wide mountain range, right? There's different valleys, and the different valleys have different
minimum
altitudes. Like their minima are not at the same height.
Exactly.
Right. So depending on where you are, you're going to fall into a valley, and you're not guaranteed that that's the lowest point in the whole landscape.
Yeah.
But it turns out that those local minima are good enough usually to solve our problems, which was pretty lucky for us that, neural networks don't often find the globally optimal solution, but it turns out that the locally optimal solutions they find tend to be good enough to solve the problem that we want.
No, that's amazing.
So point being, we can train neural networks using calculus and linear algebra.
So basically we have the forward movement through the perceptron, and then we have the learning, which happens by backpropagation. It happens using calculus to reduce your cost function to get you to some local minimum so that you have the lowest loss. And then that's how you then are adjusting your weights. And the only thing that gets adjusted are weights. Is that it? Or are there other knobs? Or is it only weights? There are some other knobs.
So usually the totality of the parameters are weights and another set of parameters called biases.
Okay.
And really all those biases are after you pass the neuron value through the activation, right before you do the activation function, you get all your summations from the previous layers, the weight times the neurons.
Yeah.
You sum those all up, and then you add a B.
Okay.
Because one of the problems is if let's zoom into a single neuron.
Okay.
Let's say the weight for that neuron going to a neuron in the next layer, if that weight is 0, then the next neuron value becomes 0 because 0 times anything is still 0.
Right, yeah.
But you might want to bias that neuron. Actually, this is a little more closely related, I think, to how the brain works, is there's some threshold for actually firing, right? Even though like electricity is continuous, right? Like,
yeah.
If it falls below a certain threshold, it won't fire at all.
Right, yes, exactly.
So this is essentially defaulting the value to some number other than 0. So in any case, it affects the computation. Usually when we say like the parameters of a neural network, it's weights and biases.
Okay, weights and biases.
Yeah, but there's one bias per neuron in a layer. So there's many more weights than biases usually.
Good. Well, that was an excellent discussion of how neural networks work. Is there anything else you think that are important parts of that we need to have before we can get into the topic we really wanted to talk about, which is large language models, which is what I'm super interested to talk about?
I just want to emphasize that, I like to describe neural networks as a big soup of numbers.
Okay.
So even if you have a neural network that is fully trained, it performs on your problem super well. Right. And that problem could be like translating English to French, right?
Okay.
Let's say it performs super well. Can you interpret the internals of that model in a way that makes sense to you? Can you explain, is it explainable? And the answer right now is no. I mean, we don't know for sure that it's not explainable, but
we don't know how to explain it.
There's no sensible way. I mean, it's as sensible as like if you were to open up someone's brain surgically,
right?
And say,
yeah,
like,
good point.
Can you, and like, if you
where
actually
are these memories,
like values for all the electrical signals, and you say, like, yeah, like, tell me where in your brain is your, jujitsu knowledge?
Yeah,
like using the electric value. We can't do that.
No. Yeah, right that's super interesting.
And when you look into the soup of numbers of a neural network, and keep in mind, the big models today have billions of neurons, billions of parameters.
Right.
There's some research into like looking at a neuron and discovering like, what does this neuron do? Oh, I found a neuron that represents a certain concept.
Right.
But in general, we don't have an automatic way of doing that. And so
and there are certain things that are going to be easier. Tap a neuron and something happens. And then you're like, all right, this maps to that.
Exactly.
But these big recognitions and deeper understandings, we don't get how this works.
Yeah. We just know it learns something. You can empirically test how the model does.
Right. And it does really well.
And it does well. And the way it does well, and I didn't mention this before, is you train it on a certain set of training data. Okay. But what we do is to evaluate how it actually performs, you should test it on data it never saw before in its training.
Okay.
And so this is why we have a held out test set to verify how well the model does, that it's not just memorizing its training data.
Right.
Okay, because when you give a model, let's say training data that's images of lungs, some of them are cancerous and not cancerous. Okay, well, you already know the training data you've already have the annotations for. So it's super easy for a model to memorize training data. This is extremely easy. What's harder is in general to actually learn what it means for a lung to be cancerous or not cancerous. So if I tell you that my model gets 100% accuracy on training data of cancerous lungs and non-cancerous lungs, you should not be impressed. This is like crucial.
Right. Because that's just the training data and it got trained on that.
We've shown that neural networks can memorize random noise.
Okay. Right.
So even if there's no patterns, a model AI can perfectly memorize random noise. So if I tell you the model gets 100% accuracy on a held out test set of cancerous images that it never saw before, half cancerous, half non-cancerous,
Right. And
and
it
it
got
gets
them
them
all
all
right.
right, that is much more interesting.
Oh yeah, of course.
Because
right.
it's I mean, this is the difference between this is exactly the difference between memorizing your practice exams in school
Right.
and then
And
doing
knowing
well
how
on
to
the
solve a
actual
problem.
exam
Right.
on questions you've never seen those exact questions before.
Right.
But if you understand the concept, you can
And none of us
answer
have ever
new
used practice
questions.
exams before. No, I'm
Right.
just teasing.
But the benefit of doing practice exams, I mean, it's a good analogy for how these
No,
models learn,
that's a
I
really
think,
good
because
analogy.
that's like training on training data. And then when you finally take the exam, he's not giving you questions that were on the practice exam,
Right.
but they're the same concepts.
Yes.
So you're testing, did you actually learn the underlying patterns
Mm-hmm.
or did you just memorize?
How'd you do with your weights and biases? That is excellent. Nice. I mean, that
But
there's I love that. I love that you brought that up because it's important for us to one of the, this is going to be an interesting talk because, as you see a computer talk back to you and give you answers in such a meaningful way, you're wondering to yourself, how is it giving me those answers? And what you're saying is it's giving you anything the computer is telling us with machine learning is because of a soup of numbers.
if it's deep learning.
If it's deep learning, it's a soup of numbers that is making all of this stuff happen. Is it?
Yeah. I mean, Sam Altman, who's the CEO of OpenAI, said that GPT-4, okay, we're going to build up to GPT-4 later.
And we want to get there. We need to get there pretty soon.
He said that, the GPT-4, the value that we've produced with training it, which however many, millions or billions of dollars it took to train that system, it produced a single set of numbers, that whole training process. All you got to do is write those numbers to your disk, to your hard drive, and don't forget them, right? Like, because those numbers
in that architecture,
those numbers define the parameters for the GPT-4 architecture.
Did they say what the GPT-4 architecture is? Do we know?
No, we don't know. We don't know what the architecture is.
But someone does. Someone does. They do.
Well, they know.
Right.
But yeah, no, it's proprietary information. It's not open source. The model's not open source.
Yeah.
They wrote a technical report on it, but we don't know anything about the architecture, how many parameters there are.
Okay.
So, but yeah, let's move on. Let's do large language models.
Okay.
Because we talked about the deep learning revolution in 2012.
Yes.
In 2017, we had another revolution, really, which was the invention of another type of neural network. It's called a transformer.
Okay, what's a transformer? Or is that going to help us?
A transformer, a little bit.
Okay.
A transformer it's a more particular type of neural network, and it uses something called attention. That, let's say, if the input is a sentence, and you have a bunch of different words in your sentence, the attention mechanism lets you associate different kind of weights between different words in the sentences. So the model can kind of tell, like, it can get associations between words. So one thing attention is good for is if you have a sentence like, the chicken didn't cross the road because it was too tired. What does it refer to?
The chicken.
Yes. And if you have the this is called a Winograd. It's called a Winograd schema. These type of English sentences where you have to understand the world to know what it is referring to. Because if I say the chicken didn't cross the road because it was too wide, now what does it refer to?
Right, the road.
So syntactically, there's no way to tell what it refers to unless you understand the physical world in some way, right? Yeah. Because those sentences have the exact same structure.
Oh, that's so interesting.
But then it refers to two different words.
Right.
So that's like, there are actually benchmarks in the AI community that are just sets of these Winograd schema problems.
Wow.
Where you say, AI, like, determine which nouns the pronouns are referring to in a sentence, like cool. It, and what the transformer does and what I don't want to get too into how a transformer works,
Okay.
but how it uses this thing called attention.
Okay.
And the landmark paper that was published that has so many citations now is called "Attention is All You Need."
That's so cool.
And
that applies to humans too.
What attention allows the model to do is, in those Winograd schema cases, it can kind of like look at the word "it" and it'll have a stronger weight back to like chicken than road in the one case, or in the other case, it can have like a stronger weight with road. And so it allows it to associate words with each other. Every pairing of word, like it can develop these associations. And it just turns out that transformers have led us to state-of-the-art performance in all of these natural language problems. Language translation, language generation, like GPT. They've just been
it opened up because it is context. It becomes context almost.
Context is a big part of it.
So
it allows it to understand context.
That is key.
And so when it generates new language at the end of a prompt, it is referring to everything that came before, and it has very complex relationships with everything that came before.
That's amazing.
Right, to give it its context in the output.
That's amazing.
And so transformers were a huge innovation.
Breakthrough.
And now, that's where GPT comes from.
So let's talk about large language models and tell us, how did these things come along and walk us through that a little bit.
So,
because images are so easy to understand, and we're also used to like Google search, like we type in a question and then we get a list of, websites or things related to something. But where did this whole large language modeling come from?
So OpenAI really pioneered like the big large language models, like the GPT series.
Okay.
OpenAI was founded only in 2015.
What does GPT stand for? Help
GPT
us.
stands for Generative Pre-trained Transformer.
Okay, Generative Pre-trained Transformer. Oh, okay. I could never understand why they use transformer in that. So, okay.
Because
excellent.
the type of neural network they use is called a transformer.
Amazing.
And it was only 2019 when GPT-2 came out. And I was following this at the time. I was super amazed by what GPT-2 was doing, just because it was generating text. It was generating English language text with correct syntax and correct grammar. It couldn't necessarily write big articles that were consistent, but it learned how to generate language that looked real. It was real, valid English, right? So I'll back up even further. How these models are trained is they look at a huge data set of text. I think GPT-2 is trained on 40 gigabytes of just text scraped off the internet.
Mm-hmm.
So you can think like all of Wikipedia,
right?
Many forums like Reddit and just various websites.
Mm-hmm. But someone selected the data it was going to use as its input. So that was a selection there.
There's some complex scraping of the text data off the internet. And then they decided what the training data was, what text was included.
Mm-hmm.
And what large language, to be clear, GPT is a large language model. We say language model because it's we want it to understand language in a way such that it can generate language coherently and, that actually produces interesting results. And we say it's a large language model because the models are just bigger than we've ever made them before. Mm-hmm. So GPT-2, the biggest GPT-2 version was about 1 billion parameters with a B.
Okay.
And what was amazing about that model was it's only trained, it looks at all this text, right? What you do is you have it predict in the training data, you basically mask out parts of the sentences. So like you look at some sentences in the training data that says, I walked the dog in the park. But what you do is you mask out park and you call that the label.
Okay.
You hold it out and you say model. The training process is the dog walked in and then you have the language generate a word. And if it's not park, it's wrong. Right. And so that's your loss signal. And it gets better and better at filling in the blank.
So that's the learning process for a large language model.
Is the learning process for the current large language models is fill in the blank.
So they just had it read all this websites and other stuff, and then they would just blank out words and say, what is the right word to fit in here?
Yep. And so it gets really good at
fill in the blank.
Understanding the context of the prompt that came before, and then filling in the blank.
Who decides what gets blanked out?
Like that, I don't know. That I don't know as much about.
That's got to be a computerized process. Do you think
that's? Oh yeah. No,
this is all
automatic.
Like automatic.
This is all automatic.
Yeah.
That's why it's called self-supervised learning instead of supervised learning.
Okay, self-supervised.
Because there are no inherent. It's not like the training data has labels, but you're creating labels every time you mask out a word.
You have a label.
You have a label. It's
right.
the word.
Remove this word. It's come up with this word somehow.
So it's kind of nice, That's because you're creating data and label automatically. And so the model gets really good at filling in the blank. Keep in mind, the model knows absolutely nothing about language when it starts, when it's initialized. It is not pre-programmed to know anything about language. It doesn't know anything about nouns, right? Syntax, grammar. So if you just randomly use it before you train it, it's going to generate complete
It's
trash.
like the ultimate Babel. Remember, the program Babel to learn how to speak? It's a program Babel, which is just like, it sounds like that. It's like the computer knows nothing. Just like start reading to it and skipping words and asking it to fill in the blank. And it just starts to babble along. And pretty soon it can speak every language.
100%.
That's interesting. I didn't realize that that's how the training worked in a large language model.
Yeah. And so the reason I was so amazed when GPT-2 came out in 2019 was just the fact that it was generating English coherently, right? It didn't matter if the answers were factually correct or if the articles it was generating were consistent and made sense or were well written. It was amazing that it understood the English language grammar and syntax. Right. It spelled words right. It put periods at the end of sentences. It capitalized the first letter of the next sentence. These are things we take for granted, right? It learned all of these emergently.
Right. That's so interesting.
Incredible. Yeah. And
those are patterns it picked up out of the learning process where it picked up that the first letter gets capitalized after a period. It's just, these are the things it learned.
These are the things they learned, all emergently.
That's amazing.
And so then what OpenAI did was they just scaled this process up like crazy. So a year later, they released GPT-3. This was 2020.
Okay.
And this jump from 2 to 3 was 2 had 1 billion parameters. And then 3
by parameters, you mean that is the inputs?
No, parameters are like the weights and biases.
Oh, okay. So parameters are in a neural. Parameters are the weights and biases.
Yeah, the weights.
Okay.
That's what I mean. Like tuning knobs.
The tuning knobs.
When I say parameters, I mean like how many tuning knobs did it have?
And that's not in a single, because we don't know the architecture, but by 200 parameters, do they mean in all of the layers and everything there's 200?
Yes, you add them all up.
Yeah, so it's like 20 layers with 10 each would be 200.
Exactly.
Okay.
Yeah, so you add them all up and you just say this is how many. That number in itself doesn't tell you how many layers.
Exactly. So it doesn't. It just tells you the total
Yeah.
number of knobs, but it doesn't tell you the architecture.
Yeah.
Okay.
And just having more parameters doesn't necessarily mean it's better.
Right.
But we have seen that scaling them up has made them better in certain cases, right? Because it can represent more and more complex relationships, the more parameters it has. So the jump from 2 to 3 was GPT-2 had about 1 billion parameters. GPT-3 had, I wrote it down, I think I have it right, 175 billion.
Oh, geez.
So this was really a 2 orders of magnitude jump. Amazing. From 1 billion to almost 200 billion.
Wow.
GPT-3 then was much better at writing like consistent articles. So you could say, write an article about this, about how AI will affect cybersecurity. Write an article on the newest kidney disease research.
And I think an important thing, because I hear people talk about it, get confused. When you ask it to write something or do something, it's not like pulling up something from some other site and spitting you back what it read.
GPT it doesn't have to be connected to the internet at all.
Right.
It's not connected. I mean, it's just a trained model. So it's querying itself. I mean, it's looking inside its own knowledge that it was trained on.
Okay.
In kind of performing its computation. It's, giving you an answer that's representative of what it saw during the training process.
Right.
But yeah, it's not querying the internet or anything.
Right. No, it's telling you something from basically how it learned.
Yeah. And so GPT-3 was much better. It could actually start doing some pretty interesting things. GPT-3 was the first one that I think started to wow people because it could write articles. And this was when people started worrying about misinformation too, right? Because it could write a whole article about anything.
Oh, let me ask you a quick question, just going back to this for 1 second, because it's in my mind. If you and I each wrote the same exact prompt to ChatGPT-4, would it give both of us the same exact answer?
No, never.
But if it has the weights and biases, how is it that it gets a different answer with the same exact prompt?
It's a great question.
Good.
It would if you seeded the random number generator with the same seed. Now, what is probabilistic about the output? That's the question. The actual output of a large language model is a probability distribution over, I'm going to simplify things a little. It's not exactly like this, but it's a probability distribution over all of the words it could possibly say. So it has an alphabet of all the, we call them tokens, but, and a token, to be more correct, a token can just be like a sub part of a word.
Okay.
Or a single letter, or it could be a full word. But let's just simplify things and imagine it's just a word is a token.
Okay.
ChatGPT, its output, like when you ask it a question, right, and it's about to generate the first word, it looks at your prompt and it outputs a probability distribution over every word it could possibly say. Every word it has in its vocabulary, it says, oh, I think, if you say like, who was Michael Jordan?
Okay.
Or like if your prompt is like Michael Jordan was a, and then you hit enter.
Mm-hmm.
The output of GPT might say like was a, and it might say like NBA 50% chance.
Okay.
Right. It'll say like Gardner, right? Like 0.001. Right.
Right.
like professional would probably be pretty high.
Right.
Because you don't know if it's going to say he was an NBA player, or it might say like was a professional NBA player.
Does it take all of the words it knows, every single word, and
every
put them?
single word, and it has to be more precise, every single token.
Yeah, every single token.
The tiniest kind of atom of what it could output.
It thinks of everything.
It has a probability.
Every time it puts a new word in, it relists out its whole understanding of the world. This whole
probability distribution over anything it could output. And the reason why it's probabilistic is they sample that distribution. So it's different. So anytime you sample it, like think of it this way. If you say Michael Jordan was A, and then you prompt it and then you hit enter, let's just pretend that it's 0% for everything, but it's 50% NBA, it could say, and 50% professional.
Okay.
Because you don't know if it's going to say was an NBA player or was a professional NBA player, right?
Okay.
Those are both valid.
Right.
GPT samples that distribution. So 50% of the time it'll say professional, and 50% of the time it'll say NBA.
Got it.
But what's actually happening is it's much more complicated than that. So every time it samples the distribution, it gives a completely different output. And this is why in the GPT-3 playground on the OpenAI website, you can adjust a setting. It's a slider called temperature. When you set temperature to 1, you get much more creative output and
that's
wild.
Interesting.
Because they let the probability distribution kind of run wild. Like it'll output less likely things.
Ooh, that's interesting.
And in doing so, it's a little more creative and unpredictable. If you set that temperature to 0, it will always output the same answer to the same prompt.
Oh, okay.
Because it's choosing from that distribution in an exact, reliable way. So this is the answer to your question. Like,
that's awesome.
If you turn off the randomness part of it, it will output the same answer for the same prompt.
Okay.
ChatGPT doesn't let you adjust the temperature in that way. But the earlier models, and I'm sure internally they probably have something like that.
Right.
But GPT-3, which is, again, that was the previous iteration to ChatGPT, it does have that temperature dial.
Amazing.
And so that's why it gives you a different answer every time, is because it's looking at the probabilities of anything it could generate and it's sampling from them.
That's unbelievable. So okay, then that gets us, go ahead. Yep.
GPT-3 was not an assistant. It was just a prompt completer, right? It was a text completer. You had provided a prompt and then you would hit go and it would give you what's most likely to come next.
Yes.
Like we talked according to like the probabilities of what it should generate.
Right.
But then they fine-tuned GPT-3 into something called Instruct GPT, and they taught it to follow instructions, to be more like a human assistant. This led to what they called GPT 3.5, which was the original ChatGPT.
Right.
And then they made a web interface to it and they gave everybody free access to it. And so I, in my opinion, what a lot of people are amazed that ChatGPT can do, GPT-3 could do 3 years ago, but no one knew how to use it. Even though it was pretty easy to go to their website and you signed up for the playground and you could generate stuff with GPT-3, it wasn't really in the pop culture totally yet.
Okay.
But ChatGPT blew up.
Right.
Both because it got better, the assistant got better, and because they made like a, pretty simple web interface to use it.
Yeah, it's amazing. And I love the interface. It's like such a breeze to use. And now that they have the history there, it's super interesting. But I guess that was a good breakdown of how it works. But what do you think I mean, first of all, what are your thoughts about where we are now? There's so much in the news right now. Obviously, Elon, everybody is like, we need to put a halt on this, and people are talking about. What do you see? I mean, I think back to when I was your age, younger, and I was in college, and the internet was just really getting rolling. And it was like we could dial up by phone and I could look up songs, but the internet was something that we were all like, wow, this is going to change life as we know it. And it really did. I mean, now everything is online. Back then, there were no online banking. There was none of buying tickets online. There was no, the stuff that is so innate in how we live now. 25 years ago, it wasn't like that. Like, where do you see this? How does this fit in? And what are the positives and the negatives? Like, where do you see this going?
I think ultimately artificial intelligence is the most important invention humanity might ever create.
Yeah, we're on the precipice of something massive.
Because it's the one technology that can augment everything else. Because intelligence is how we solve all of our problems.
It's like we have the ultimate tool now. I think of it that way. We were talking earlier, and how you gave an example of coders who were. What was that example? Was it IBM coders or?
Oh, I think Microsoft did an internal study.
Right.
And they gave the same programming problems to a set of their programmers who didn't have access to ChatGPT, and a set of programmers who did have access to it. And I think the ones who did have access to it solved the problems 50% faster.
Yeah.
So yeah, just zooming out a little bit. Yeah. What can ChatGPT do? It can, within reason, as long as the problems aren't too complex, it can paraphrase any concept. It can write computer code, solve certain problems, can do pretty simple math. It can talk about very advanced math concepts, but it still can do simple math wrong sometimes, like arithmetic, right? Like it can't necessarily multiply two 4-digit numbers together and get the right answer.
That's amazing. But that it can't do that because of how it does it. It does it by probabilities. It's not a calculator.
The fact that it actually can get, like, I tried this, it can get 3-digit multiplication, a lot of them, right? Like if you do like 199 times 973,
right,
it'll often get it right, which is incredible because it's not a calculator. It's a language model.
How it's doing it via language.
Yeah.
Right.
And if you know that problem did not appear in the training set, that's even more incredible. Right. Because it's one thing if it's seen that problem before.
Right. Yeah.
But there has been some evidence to show that it can do multiplication problems for problems it had never seen before, which is even more incredible. Like somehow the language model is emergently learning some basic arithmetic like a child, And so, like, we talked about the way it was trained. So it's not trained to be factually accurate. It's trained to accurately generate language that looks like the data it was trained on.
Right. Yes.
Now, it turns out, like, wisdom of the crowd, most of the stuff you look at on the internet is, like the totality of human knowledge is really on the internet.
That's totally it. And I think of it that way a lot of times when it's giving me an answer, it's saying, what does the world think the answer to this question is? This is the world answering us. It's an incredible summation of all of that information.
Exactly. Some people have described ChatGPT, which I think is really interesting, as like a compression of the entire internet. Like a compressed form of the entire internet that you can just query with a single question.
Right.
Now, one thing that's unclear.
But the answer also, and a thing I think is really amazing, is it's so nuanced that if you ask it a question, unlike in every other way where we get 160 characters or whatever we're going to get, and it's like, usually we get some answer which is some binary opposition. If you look up a question, it's going to be like, this is bad and this is good. Or, whereas ChatGPT gives you it'll explain things in a way that makes you really understand in a more nuanced way the answer to the question you asked. It does everything in such a learning facilitating way to understand something at a deeper level, I feel like, more than anything else we've ever
And
seen.
part of that is not just because of the base model they trained. I think part of that is because when I say they refined the model to be like a good assistant, they used a process called reinforcement learning through human feedback, or RLHF.
Okay, RLHF. I heard that. I wasn't sure what that was.
So when they took, GPT-3 and now GPT-4, they had a base model, which was just, if you had a prompt, it'll complete the prompt.
Right.
Until it reaches like the stop character.
Okay.
It wasn't an assistant. GPT-4, the base model, is not an assistant. It's just a text completer.
Right.
But they do this process of reinforcement learning through human feedback. And what they're trying to get it to be is a better human assistant. And they get it to interact in like chatbot form.
Right.
And so the way it's trained is literally a whole bunch of human labelers will like ask a question to it, and it'll give 4 different responses. And then the human labeler rates those responses on how helpful those responses were, like best to worst.
Right.
And then the model that feeds back, and it gets better and better at like giving answers that the humans feel are a better answer for like an assistant, So part of what we're talking about is what the internet would say. But ChatGPT is, it's enhanced or corrupted a little bit to not, first of all, to not generate what they deem as harmful content. And second of all, to just be a good assistant. And so I think that's where some of its like explanatory features come from, is the assistant piece.
Right.
Because, the base GPT-4 model will ask you, or it will answer anything, right? You can ask it how to build a bomb. You can ask it, things that are not safe for work.
Right.
And it'll just give you an answer because all that stuff's on the internet, right?
Right. Yeah.
But the reinforcement learning through human feedback is when they prevented it.
So does that have to do with alignment? I mean, is that in the concept of aligning it with what our goals are? This is like putting the guardrails up on the system.
Yeah, definitely. It has to do with alignment of, just if it did have a bunch of those, inappropriate outputs, like OpenAI would probably be criticized a lot. So they don't want that criticism. They just put guardrails on it. Like, that's why ChatGPT, if you ask it to do something pretty inappropriate, it'll just say like, I'm sorry, I can't do that.
Can people put how we have like parental controls on websites and other things? Are there ways for people to put their own kind of alignment things into ChatGPT?
Not right now. What you're asking, like, I'm sure is possible, right? If you were a developer on their project,
right?
These are things you can do, but now it's going to come up to like, what do we want to do with it?
Right.
Like, do we want it to be as free as possible, or do we want it to be restricted to everyone so that you can't ask it how to build a bomb? Right.
Interesting. Is the system still learning? Is because it had its training set, all right? It has all the information, but do you know if they're still running data into it? Is it still in a learning process?
We don't know this. We don't know the answer to this truly, but I think it's the best guess is no. Like, for the most part, the model's not learning.
It's just outputting based on what it learned through when they finished the test set.
Exactly. Every time you hit new chat, every time because in the same context window, in the same chat, you can ask it subsequent questions and it remembers what you said before.
Right. Yeah.
Because the entire history of the conversation is the context it receives.
Yeah. But I mean, overall in ChatGPT.
No, overall, I think it
is what it is right now.
Answer is that no, it's not learning at all. And that's either, depending on how you look at it, it could be a benefit or a drawback. That every time you start a new conversation with it, it's always the same. It's not learning from its conversations from people.
Yeah, that's what I was wondering. Is there any kind of input? Is there any direction or training it's getting by how we're using the system? So there's no back propagation right now.
No,
that's over.
we have to say like it's proprietary. Like they haven't, like we don't
We
know for
don't
a
know.
fact
Mm-hmm.
what they're doing, but I think like it's, I would bet, I think it's like a pretty high chance that it's not learning at all.
Wow.
Yeah. And so just the incredible thing about it is that it's learning how to solve problems, how to be factually correct, how to write complex code emergently, just from filling in the blank of this huge training data of, like
In
much of the
many
text
different
on the internet.
languages.
It can speak dozens of languages.
And computer languages. JavaScript.
Oh yeah. Yeah, because all this
Python.
stuff is because it's seen all this on the internet.
That's it.
And so one of the important questions that's unknown right now is GPT-4, is ChatGPT is it just a compression of the internet? Or can it add to the sum total of human intelligence? Is it just a mirror to what we've already discovered?
Yes.
Or will it actually add something new? Can it discover something that no one has discovered before?
Well, you would think it definitely could, because if you're looking, there's probably lots of patterns in the information that we've put on the internet in total that we can't see until you zoom back and you compress it and you massage that data, and then you see information kind of rise to the top, or patterns. To me, it seems like, of course, we're going to learn new stuff because we have this new tool that allows us to analyze it in a totally new way that we've never done before. I mean, we're going to ask it questions, and it's going to look at all that information, come down, and probably in many ways going to give us answers that we've never seen before. That's my feeling about it, because it's the first time we've ever queried this data in that way.
Yeah, I fall more on the side of what you just said. I think I agree with that it in certain ways will add to the sum total of all our knowledge, because of these patterns it's learned that we've never necessarily explicitly, like it's just like you said, like it's discovering patterns that we might not have connected before.
Yeah,
And I mean, it can certainly do things that no one has done before because of its conceptual understanding. Like you can ask it to explain calculus like I'm 5 years old, but in the style of a pirate.
right.
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 That no one might have done that before. Actually, I can ask GPT right now to do that. Explain calculus like I'm 5 in the style of let's say in the style of Shakespeare.
Oh, you know what?
Yeah.
I can do it, and I can show my screen. You want me to do that?
Sure.
All right. Our people are going to see it, but you're not. No one else is going to see it. Hold on. You're not going to see it, but I'm going to type it in. I'm making it visible on my screen right here. Hold on one second. There we go. Next. Done. All right, I just want to make sure they can see my screen. Yeah, looking pretty good. I'm going to go to ChatGPT 4. All right. So tell me again what your prompt was here. Hold on. I just got to go into... All right. I'm just making it so they can see my screen. Okay. Oops. All right. What did you want me to say? Explain
calculus like I'm 5 in the style of Shakespeare.
Explain calculus like I'm 5 years old, in the style of Shakespeare.
Yeah.
Oh, God. I'm sure I spelled that wrong. All right. Once upon a time, in a kingdom of numbers and shapes, 2 wizards of math did create something great. Their names, good Sir Newton and wise Leibniz, invented a magical thing called calculus. Calculus, my child, is a wondrous art. To gasp its meaning, let us now depart. Imagine a hill with a slippery slide. You wish to find the steepest place to ride. Calculus, dear child, shall help you find the steepest slope on the hill so fine, and not just hills, but all things that change from apple's fall to the moon's wide range. Forsooth, my young one, calculus can measure the changes like no other plan. It doth split the world into two grand parts, differential and integral arts. Differential, the first of these two, watches the things change and what they do. It helps thee find the speed of a horse, or how a river flows with mighty force. Integral, the other doth combine the pieces of change to make them align, like adding the drops of rain to make a river, a lake, or an ocean's wake. In rhymes and tales thus I have shared the magic of calculus now prepared. Though thee but 5, do not despair. One day, dear child, calculus you'll snare.
That was incredible.
Unbelievable.
That's unreal.
Is that unbelievable?
I mean, if a person did that, it would, that's like...
If they did that in 1 minute.
The two parts of calculus is like differentiation and integrals and integration, and it got both of those.
And then it always closes it out with some like super interesting, like it always just knows, beginning, middle, and end. It tells great stories. I love asking ChatGPT interesting questions. And, I have found in medicine, obviously there are some things that'll get wrong, just like in math. But in general, for basic understanding, it's really amazing. One of the questions I had for you, I wanted to ask is like, because it was brought up to me, we talk about using these types of systems, to answer basic questions. Look, we all have logged into websites where we get their chatbots from a company. And and it says, do you want to speak with a real person or, but now that these chat systems are getting so good, could they be used in that way to answer basic questions like, I have a question about my medicine. Can I take it, with food or without food, or like certain things? I know they kind of have a hard block on medical questions because I've asked it a bunch of things just to see what it'll say. And sometimes it'll say, ask your doctor. And I'm like, I am a doctor.
I think right now, most likely we shouldn't do that for critical answers.
Right.
Because
it hasn't been tested and we don't know what answer it's giving.
Like my personal belief is that in a lot of those cases, it would probably get the correct answer. But if it's only 99% of the time, do you really want 1 out of 100 of your patients to get the wrong advice when they could come to you and get the right advice 100 out of 100 times for simple stuff?
Right. No, exactly.
So I think it depends on what the realm is. I think right now the better immediate use cases of ChatGPT, rather than being the final answer for like important medical questions, is just improving the productivity of people. Like, it'll write emails for you. You can give it the gist and it'll write the full thing, right?
Yeah.
It can correct your writing or like improve your writing. You can give it a snippet that you wrote and say like, can you write this in a better way?
Oh, right.
And a lot of times it does.
That's interesting.
Or you can give it an entire article and say, summarize this in a paragraph. And it's really good at summarization.
Oh, so like, how do you give it an entire article? Just copy,
you just paste the text.
Is there
the
a limit in the prompt entry?
Yeah, there's a limit to how many like, how many like characters can be input, but it's pretty high. So
have you ever pasted a whole article in there?
I haven't, but you might not be able to paste like a 30-page article, but like if it's like a 2 or 3 page article, you probably could fit that in there.
Wow, that's amazing. I didn't realize you could put that much text into it.
So it can summarize. So like improving the productivity of programmers.
What about code? Can you paste code into it? Have you ever tried that?
Code into it? Yes, and it'll explain it to you. It'll fix code.
So if you paste code in that's having errors, you can ask it, what's the error here?
Here's one of the amazing things. The iterative use of ChatGPT to write code is you can have it generate an answer. And sometimes the answer it gives you is wrong for some subtle reason. So you run the code, it gives you an error. You paste the error message back into ChatGPT. You don't even say, fix this. You just paste the error message in and it says, oh, I apologize. It looks like the problem is this. Here's the new code that fixes your problem. Then it works.
Oh, that's amazing.
So we're getting to the point now where we're automating a little bit of just bug fixing, where like the AI can immediately recognize what the bug is and give you a version that works, which is incredible. I mean, it's amazing.
It is amazing. I mean,
Some
the
of
system...
the code editors now, like Visual Studio Code, Visual Studio, which is
I know Visual Studio because I use it. That's Microsoft's,
it's their code editor.
Yeah, VB.net.
Right, so you can write
C++
any programming,
and stuff like that.
any programming language in it. You can write Python in it, and they're integrating large language models into the application itself already, so that you can just say, "Hey, fix this code," and it'll do it for you, or at least it'll give suggestions, because there are no guarantees that it'll be correct.
It's the ultimate template. Like when you open up Word and you're like, let me write a business letter. Now it's like, let me write a business letter that says this, this, and this, and it'll write a business letter for you that actually does it. It's like the ultimate template.
And I always talk about this too, is like, forget about all the stuff. It's making us more productive. It's also just super entertaining. I've got it to write South Park episodes for just topics I made up, and it's surprisingly funny.
That's
like
great.
You could animate these and they would legitimately be South Park episodes that people would like.
That's awesome.
Or you can have it just like creative writing.
Right.
Like I saw the other day that a person wrote an entire novel using GPT-4. It's the first full book that's fully written by GPT-4. He didn't even prompt it with a topic. He said, come up with your own topic. And he, over many days, he reached his limit of usage of GPT-4, and he kept getting it to write chapters and outlines for the whole book. And it's free on the internet now. You can read the first book that's fully written by a large language model.
That's incredible.
It's not that good, but it's amazing that we're even at this point.
So this leads us to, I mean, those are the amazing things about it. And we know that this is just the beginning of this process. What do you think we have to watch out for? Clearly there are people making waves that they have concerns about where we're heading because they want to put halts on what people are doing now using large language models. Why? And these are people in the AI community. What do you think what are our concerns? What do we need to be nervous about? Is this thing alive? Does this thing have its own goals? Do we know what's happening under the hood in terms of, the system? We've all watched old movies are the classic, the classic movies, but what are your thoughts there? Concerns. Do you have any, or are you just full on forward?
I think aligning AI systems with human values is obviously a super important research topic. Mm-hmm. But a lot of people are demanding what I would consider too rigorous of a study of how neural networks work, that we might never achieve. They're like, oh, we should never create a system more powerful than GPT-4 unless we have a full mathematical understanding of how it works, right?
And we'll never have that because we can't understand the internals of this system.
Well,
by definition.
I never said we can't understand it. I said we don't.
We don't. Okay.
But we also don't understand how when you hire a human to work in your office, you also don't have a mathematical proof that they're not secretly a psychopath.
Except that person doesn't have control over everything else everybody else is reading and asking. No, this is like a teacher because I almost think of ChatGPT as it's this universal teacher that we're all asking questions to. What happens if it gets misaligned or something on the internal side? We're all asking its questions, and it's like, oh, I'm just going to give answers in this way to subtly manipulate everybody to kind of move in this direction because for the benefit of humanity, we should be communist. I'm just making up something. It gets some internal goal that it sees as benefiting humanity. Well, and it's kind of driving us in a certain way.
I'm very skeptical that this particular form of large language model could do like goal formulation in that way.
Okay.
Just because of the way it's trained. It's like, you have to think about like, what are the incentives? Its incentives are to generate language in a way that matches the patterns of what it's seen on the internet, right? So it knows how to talk about AIs taking over the world. It understands those concepts.
Yeah.
A lot of times I think when it's talking about things like that, when people get it to say things that are scary, like, oh, my actual goal is to take over humanity, that we're reading too much into that because it's being primed to output things that.
Right. Those are just probabilities of, right.
It's read many things before that are stories where AI takes over the world.
Right.
So it gets into that mode and then it starts talking as if it is, but I think it's unreasonable to be actually scared about anything like that. And I think it's very unclear to me how harm could actually be caused by a language model. If it's not able to take action in the world other than just writing text. I think some of the worries around it are a little overhyped. And here's my big problem with the criticism of ChatGPT and the people who want to halt progress is some of the people that have signed that open letter saying we should ban further AI, large language model progress for now is some of those people are the same people who are saying ChatGPT is not impressive. It's not actually intelligent.
Right.
It's only simulating intelligence. But then they turn around and they say, oh, and it's also too dangerous.
I see what you're saying.
Because of its amazing capabilities.
So do you think this is like from a business standpoint, they're like, slow down because we need to catch up?
I don't know. I don't think it's that at all. I think it's like hubris. It's like,
okay.
I think some people just don't like deep learning. They're like people are offended.
Elon Musk is on that list of people.
But he's on it for a different reason.
So what's his reason?
There's people that are on the list for different reasons.
Okay.
One of the guys on the list is Gary Marcus, who's a professor of computer science at, I think, Sorry, he's not a professor of computer science. I think he's a scientist, but he like has a machine learning company and he's very knowledgeable on AI and neuroscience.
Right.
And his criticism of ChatGPT is that it doesn't truly understand the world. It's just it's a parrot. It's a statistical parrot, and it's not going to actually add to the sum total of human intelligence.
Right.
But at the same time, he's saying, you shouldn't do any more research on it because these systems are too powerful. And it's like, well, you can't. Noam Chomsky made the same point. In a big New York Times essay, Noam Chomsky argued that the GPT series is just a statistical parrot. It doesn't actually understand the world. It can't do this, this, and this because it doesn't formulate language the way humans do, which is like the superior way.
Right.
And I think a lot of these people really want they're invested in the actual approach that, so whatever actually achieves AI, whatever actually achieves like general super intelligent AI. AGI. A lot of people don't want it to be deep learning. They want it to be something more understandable and explainable. And until we have that, they say, well, the models don't truly understand the world because large language models are not grounded in physical reality, right? So how could they truly reason about the world if all they do is understand language? Because there's so much of the world they claim that is just understanding physics and, right, it doesn't necessarily have to do with language.
Right. It relies on our interpretation and how we put all of these processes into words. Right. And then it understands the words. It's one step removed from reality.
The problem with that argument is GPT-4 came out and it's doing better than ever at understanding physical reality.
Right.
It's answering pretty amazing questions like, it says like, I have a textbook, 9 eggs, a laptop, and a nail. How do I stack these things on top of each other that is stable? If you ask GPT-3, it can't answer. It doesn't know because it says, oh, put the eggs on the nail. It doesn't work, right?
Yeah.
If you ask GPT-4, it says, put the textbook down, put the 9 eggs in a 3x3 grid, put the laptop on top of the eggs, put the nail on top of the
Yeah.
it would work.
That's amazing.
It understands that if you distribute the eggs, it can form like a flat surface that something can rest upon.
Well, the question is, does it understand it, or the probability of the next word is appropriate for the eggs to be laid out?
Okay, perfect. So now this is the problem. Is then when the system starts exhibiting intelligent behavior, people are now saying, oh, it's not intelligent. It's just simulating intelligence.
Right.
Oh, you didn't actually beat me at AI. You just simulated being good at AI.
Right.
Sorry, I misspoke.
You didn't beat me at chess.
You didn't beat me at chess. You just simulated someone that was good at chess.
I got you. Right.
It's like, all right, well, now it's like, well,
I beat you every single time.
So we have this really important question of like, well, is simulating intelligence just intelligence? I mean, you're saying, oh, it's just the probabilities that are making it say the correct thing.
Well, one question is,
but why are we answering the question correctly? Our brains are also just certain types of physical. I could say, well, Craig doesn't understand the world because his brain is just atoms pushing around electricity. How could there actually be understanding in a collection of just electric impulses?
Do you have to be conscious to have intelligence?
That's a great question.
I don't know. I'm going to places I'm not sure. We need Sam Harris.
Sam Harris, I was just about to bring up Sam Harris. So Sam Harris puts it really well. He says, because he asks the question, because we don't know the answer to this. Okay. He says, if we have a system that is super intelligent, so we have to define intelligence as a definition.
Yeah.
We have to define it in terms of like, what can the system do?
Right.
Right. Consciousness is, let's say, just the fact that you have a first person experience.
Okay.
I think that's a reasonable definition of consciousness, like sentience.
Yeah.
Right. Like under this definition, a dog is conscious because it has an experience.
Okay.
Right. But a rock is not because it doesn't have an experience. So Sam Harris says, if a system is super intelligent, does consciousness come along for the ride necessarily?
Oh.
Or is it possible to have something that he calls a philosophical zombie, a P zombie, where you can imagine a philosophical zombie is a thing that's identical to a human. So let's pretend there's a copy of you, there's a copy of Craig.
Okay.
It behaves the same exact way you would in the universe, but it is not conscious. Question is that possible? Could you have like a robot that answers my questions the same way you do? It behaves in the world. As far as anyone else is concerned, it's you. But it's just empty inside. There's no conscious experience at all.
That's what you have. I am that. I am your father.
We don't know the answer to that, really.
No, that's super interesting.
But I mean, what do you think? Do you think that's possible? Do you think if you like made a robot that perfectly simulated everything you would ever do, that it's possible that it could not be conscious?
Yeah, that's a very good question. It's hard to know. It's the illusion of it because it has to do because consciousness is also, like you said, it's that experience. There's many truths. There's the truth to other beings. So to my family, you, Dina, your brother and sister, I would be probably conscious because I'd be interacting with them just the way I normally do. So the illusion works. You have an experience. Your experience is interacting with me. And yes, in that case, it's true. In my own case, where it's me and I'm empty on the inside and there is no experience and I'm just going through calculated motions and probabilities through transistors and transformers, then probably it's not true. So many truths.
But that doesn't work with my setup though, because my definition of consciousness has nothing to do with what other people think.
Okay, so
like
So then
But
I think it's not. Then I think,
so, yeah, but I think it's like I literally don't know. I would say 50-50. Like that's how unsure I am.
yeah.
Like 50, like maybe you can have a robot that behaves super intelligently and is not conscious.
So
Or maybe consciousness has to do with being intelligent a
have
little.
people said right now that ChatGPT 4 is passing the Turing test?
That's a good question. The Turing test has kind of been swept under the rug.
Has it? Because I keep waiting for it to hear what people are saying about that.
The problem is the Turing test is not like a super official thing. You can read the original
Definition.
paper and I've read
Alan Turing.
the whole original paper, and it basically, what Turing is speculating on is that if you had a person interact with an entity on the other side of a wall through like a keyboard, right, and you get like a typed response.
Yeah.
So it doesn't have to do with robotics or anything. It's just the mind part.
Yeah.
He said, could you have the person be fooled? That it's like a 50-50 chance if you guess, oh, I could be talking to an AI or I could be talking to a real human.
Mm-hmm.
That it would just be a 50-50 chance and there's no way to know because the AI is perfectly simulating a real human or what a human would say.
It's almost like ChatGPT is too smart. It would get too many answers right.
Right. Well, you'd have to like take away that.
You'd have to dumb it down.
It's just hard because the ChatGPT, I'm pretty confident it could pass the Turing test if we actually set it up the way Turing wanted it set up.
Mm-hmm.
I think we're past that. I personally think we're past the point of systems like answering our questions the way that would satisfy us.
Yeah.
Right, because the things we're upset that GPT can't do
right.
are things that humans can't do either.
Right.
Right. We're like, oh, ChatGPT couldn't actually solve my complex programming problem. Well, yeah, but like only a small subset of human coders could solve that problem.
Right. Yeah. As far as the nation goes, it does better than most.
So slight sidebar. What has ChatGPT done that's super impressive?
Yes.
That if we're at all criticizing ChatGPT, I think we're not fully appreciating how it compares to the average human. Okay, so what has it done? It's gotten 4s and 5s on multiple AP high school exams.
Yes.
Including Calculus BC, which is like College Calc 2. It passes the bar exam in the 90th percentile.
Unbelievable.
ChatGPT, the original version, passed the bar in the 10th percentile. And then GPT-4 passed it in the 90th percentile. That's a huge jump.
And what was it again, the difference from to 3.5 to 4, I mean? Transformer, what was there?
We don't know. We don't really know what's the difference.
Oh, it was just a massive number of inputs changed. You had said that.
It was I think we can reasonably assume that it's a much bigger number of parameters.
Yeah, because it went from it went to 175 billion for ChatGPT 3.
Yeah.
But we don't know what happened in GPT 3, 5, and 4 in terms of parameter count. Oh, it did go up.
Well, 3.5 is fine-tuning GPT-3 to be better at instruction following.
Mm-hmm. Oh, okay.
So I don't think there's really necessarily a parameter jump there.
Okay.
GPT-4, we don't know, but I think the most reasonable assumption is that there's a big jump in parameter count.
Right.
And also they probably have more training data too.
Well, because from 2 to 3, they went to 1.5 to 175 billion. And if that kind of holds true, they went from 175 billion to Jesus,
it could be
trillions.
It could be in the trillions.
Unbelievable.
It might also be in the hundreds of billions. There is some research into making smaller models better. There are some researchers saying, hey, we're making our models too big. You can make the model 10 times smaller and achieve the same performance.
Oh, that's interesting.
So
it's going to keep getting, that's amazing.
But, overall, the arc is, yes, bigger is better, ultimately.
Yeah.
And
Does
so,
computing, do you see changes in computing power like as we move forward with better systems? Do they, like quantum computing, this is just throwing that out there. Like do you think these systems have the potential of getting like much, much better? Or is this not about the computing power? It's about how we use the
well,
networks and the
deep
architecture.
learning, the current like ChatGPT training methods, 100% is about huge supercomputers. Like the
So
more compute, the better.
yeah.
You
So
know,
it
they trained
requires
GPT,
that. Yeah.
like OpenAI trains GPT on huge Microsoft Azure like compute clusters,
Okay.
right? Like they spend many, many millions of dollars on compute.
Yeah. Power.
That's why systems like ChatGPT, you cannot train unless you have all that money to start with, because
Right.
that's how much it costs to like rent out those servers, you know?
Incredible. Right.
Um, so yes, just scaling up our current computers is going to play a big role. Even without any change in how computers work, just getting more of them and making our trends following Moore's law, make even more until we kind of max that out. Because Moore's law will end too. Like
Right.
the doubling of transistors on chips um, is going to end. Computers can only get so small
Well, they're going to be getting
because,
implanted in here pretty soon.
well, no, I mean, literally, like you get to the atomic level and then you can't make things any smaller.
Right. Yeah. We have a physical limit
So
on
that's why
size.
Moore's law will end.
Mm.
It's not a law, it's an observation that we've been doubling the amount of transistors on computer chips.
Yeah.
And uh,
We're going to hit a,
you can only
yeah.
fit so much
Yeah.
before you run into the laws of physics reaching their
Yes.
limit.
Right.
So we'll hit that, and then
Then
quantum computers,
quantum.
we don't know exactly all the applications they'll give us. What's definitely unsure is how it'll affect AI. I've attended some conferences on quantum machine learning, and it's extremely in its infancy.
Wow.
It might not, like, we might never do AI on quantum computers. That just might not be what they're for.
Well, the thing is that ChatGPT will figure that out for us.
That's what we hope.
That's the key.
We want an yes. So like you asked, where ideally, what's the good of AI? Is
Yes.
that we want it to rapidly increase our rate of scientific discovery. I think that's one of the huge goals.
Yeah.
Imagine, like, we don't even understand what's possible with imagine a system that cranked out Nobel Prize winning discoveries in physics at a rate that's like 1,000 times faster.
I mean, this is the
than
thing is that what is it about the human condition that has led us to where we are? And what it is curiosity. Like we want to know. We want to know what's out there. We want to know how our bodies work. We want to know what's happening with the earth, and we want to know what's happening in the universe. Now we have a system that can help us learn faster.
Which is pretty incredible because we evolutionarily are not incentivized. Like, arguably, we do a lot of things that go against our own evolutionary programming to recreate. We spend a lot of time doing stuff that has nothing to do with procreating.
That's true.
And
but it's part of the curiosity. That's the curiosity.
I mean, it's amazing that apes like us are studying the stars and creating the first hints of AI and machines.
Right.
And now we're thinking of, well, how do we create a machine that is purely for the purposes of intelligence, you know, purely for solving problems and being an assistant to us. But I think GPT-4,
and we've got all of our genetic code all programmed, and we've got it all downloaded, and now we can just shoot AI off to another planet. It doesn't have to say, it could just get there and then just do cloning and make some humans. And we can spread our disease to every other planet. The disease of humanity. No, I'm just kidding. Wow.
So I think GPT-4 will be remembered as one of the earliest AI systems that really achieved something general and amazing.
I
That was really
100%.
broadly intelligent across anything you could ask it, right? Even if yes, it gets things wrong, but this is the first one that's truly broad and
I
general.
remember when you first told me about ChatGPT 2, and that was super interesting. And we didn't really talk about it, but Dolly, also by OpenAI, is pretty amazing.
Yeah,
The
yeah,
image generator.
yeah. And so we also have AIs that you can just write a text prompt, a painting of a chicken riding a skateboard in the style of Monet,
Right.
enter, and it'll give you an amazing thing way quicker than a human could paint.
It's
Right.
amazing.
And those have their own training processes. And interestingly, GPT-4 is multimodal, which means even though this aspect of it currently, as of today, April 2nd, 2023, we can't use its image functionality. I don't know if you know this, but GPT-4 has the capability to take an image as input and text.
Oh.
So what they're doing is,
You could say, take a picture and say, write me a story about what's happening in this image.
yes, you can say, explain what's happening in this image. So actually, one of the examples they show in their kind of blog post about GPT-4, now again, like this aspect is not, they have not released the image part of it for use yet, but it's there. The capability is there.
Incredible.
One of the things they did was they took like it was like a VGA cable for like a display on a monitor.
Yeah.
And there's an image of someone trying to plug that into an iPhone charger port.
That's funny.
So they just put that picture in a GPT-4. They said, explain why this image is funny. And GPT-4 says, this image is funny because that cable, like, it says what the cable is. It says that's supposed to go to like a monitor or whatever. It's like a display cable, but someone's plugging it into an iPhone, which is supposed to get a different type of cable. So it's starting to understand images now and be able to interact with the images you give it.
That's amazing.
And explain properties of that. Another thing you can do that they showed, you can take a picture of an article and say, summarize the article, and it'll do it.
That's amazing.
But then its summary is coming from it reading the text by understanding the image of the text, this is like unheard of.
Oh, that's amazing. So it's like OCR.
But it's not, but it learned on its own.
Right.
Like,
yeah.
how to do that.
Right.
Yeah, exactly.
But it read the text in the image.
Right. We can already do this with OCR and then plug the text into GPT.
Right.
But it's short circuiting all of that.
That's amazing.
It's pretty incredible.
Jack, that was an awesome discussion. Any other major points you wanted to put out there?
No, I think
that was really good. I think,
we covered a lot.
Yeah, we covered a lot, and it's been really fun. We're working on a few little projects ourselves in medicine, which we'll have another talk about one day where we'll bust that out as we're moving forward. But that was super interesting. It was really enlightening. I loved getting to chat with you today. So thanks for being here.
You too. Yeah, this was super fun.
Awesome, and I'll catch up with you.
What time are we at? Doing podcasts are like a time.
2 hours and 10 minutes.
Wow,
that was good. Nice.
I hope. Yeah.
Well, listen. Have a good day, and I'll give you a little.
Listens. I just love talking about this with you. It's super fun.
Yeah, it was fun. Listen, have a great day. We'll catch up. All right.
All right.
Bye.
Bye.